Hi, my name is Cidnee Luu, and I'm a master's student supervised by Dr. Mike Vanderloos and Dr. Lyndia at the University of British Columbia. And today I'll be presenting some of my work in developing a wearable EEG system. Next slide. So I'll start off by defining EEG or electroencephalography. It refers to the measurement of electrical brain activity as a voltage or potential. To measure this brain activity, the subject to be measured places on a cap with EEG electrodes attached. To allow for a good electrical connection, a conductive paste or gel is applied between the electrode and the scalp. The system measures the voltage signal from different areas of the brain depending on where the electrode is placed. EEG is very useful because of its high temporal resolution when compared to other technologies such as MRI or CT scans, which have low temporal resolution but high spatial resolution. And EEG has many applications in healthcare, including diagnosis of epilepsy, sleep disorders, and dementia. EEG has also been used in the development of brain-computer interfaces, which are systems that can use a subject's brain signal to perform a task. So this can help people with neuromuscular disorders take care of themselves with less help. I have some images here showing the use of EEG in epilepsy and sleep disorders. You can see there are abnormal changes in brain activity during epilepsy, which can be monitored to detect the onset of a seizure. In terms of sleep disorders, EEG can be used to track and look at disturbances in the different sleep stages. Overall, EEG is a safe and non-invasive way to monitor subjects and patients. However, there are some issues with current systems as well. Clinical EEG systems are expensive, require a long setup time, and they don't allow the subject to move around during measurements due to the wiring and hardware system. And motion can also create artifacts that mask the EEG signal or make the signal noisy, so these systems can't provide high quality data in scenarios with motion. And so this leads to only periodic monitoring and measurements, which in some cases may not be enough to capture the abnormalities in the brain signal. In cases of sleep monitoring, the system typically requires an overnight stay in the hospital with wires attached to the head, which can be uncomfortable. And while there are some clinical or research grade wearable EEG systems, most are expensive, on the orders of tens of thousands of dollars, and cheaper consumer grade systems may not provide accurate signals compared to clinical grade systems, which may hinder monitoring and diagnosis. Next slide, please. And so the high-level view of this project is the development of a wearable system that can mitigate motion artifacts and provide high signal quality for research on brain activity in real-world scenarios. This will allow subjects to be monitored while in motion and in the comfort of their own homes, since there's a higher likelihood that abnormalities in EEG will be detected. As well, with continuous monitoring, it will be easier to view the progression of the disorder being monitored. Currently, I'm focusing on the development of flexible low impedance dry electrodes for the EEG system and the characterization of these dry electrodes to determine the impedance at the electrode skin interface. The typical gold standard would be a gold cup or silver chloride electrode with some sort of conductive paste or gel. And this requires a lot of prep time, can be uncomfortable, and typically isn't very user-friendly. This is why I'm developing the dry electrodes, so that the procedure for measuring EEG is more efficient, comfortable, and easy for anyone to do. Shown here is a prototype of the wearable EEG system, as well as images of the traditional paste electrodes and some versions of the dry electrodes that we are currently developing. The dry electrodes are made of a polyurethane rubber, and the tips of the electrodes are coated with a silver paint. Next slide, please. And so to test and validate these electrodes, I've been using a desktop system to measure the EEG with the gold standard paste electrode and the dry electrode at similar locations on the head, and looked at the correlation between the signals as well as the power spectrum. We were able to develop electrodes with impedances in the 5 to 30 kilo ohm range, which is similar to paced electrodes, which are typically between 1 to 20 kilo ohms. And the first graph shows a comparison between the signal for the paced and dry electrode, and the second graph shows a comparison of the power spectrum between the paced and dry electrode. For the button connection type dry electrodes, the signal correlation was over 80%, which is pretty good. And so continuing on from this, we will look at using other methods to characterize these dry electrodes. For example, using impedance spectroscopy to look at the impedance of the electrodes through a range of different frequencies. And in terms of the wearable EEG system, the goal is that the device will be used not only during everyday movements and activities, but could be expanded to sports applications as well. Thank you.
Wonderful. Thank you so much, Cidnee.